So, review of last week. So we're playing around with whole number operations, and there's a few general things we're going to cover for each operation that we started last time. One is the idea of a model. And a model tells us why we should get a certain answer. So some examples of models we looked at so far for subtraction would be the takeaway model. And when I asked everyone to come up with a story, scenario kind of thing for subtraction, pretty much everybody wrote takeaway. But there are other ways to think about subtraction where it's not taking or giving something, where we just compare two things. So models are concrete. So that's something important. We can get our hands on them. I can show somebody what to do. Two, models are only good up to a certain point. So I can show you a picture of what 7 take away 3 is, or how to compare 7 and 3, but what about bigger numbers that I have to subtract, like 2017 minus 1969? I don't want to whip up blocks to do that problem. So then we need algorithms. And where models show us why the answer should be a certain way, an algorithm shows us how to get an answer, especially for bigger numbers. So let's pick on that example I just gave. 2007, so I'm missing 0. 2017 minus 1969. And I'm having trouble writing numbers today. One more time. So I had a birthday recently, and my daughter wanted to know how old I was. So I told her what year I was born in and said, you figure it out. Because she's done complex arithmetic where she has to borrow. So we have an algorithm for this, right? It's a process for getting it done. So 7 minus 9, we would all agree that's a problem, right? I can't take 9 from 7, there's not enough. So what do? I borrow, right? So I go over to that 10 right there, and I steal it, and I bring it over here, so now I have 17 ones. And in class, we use the blocks to demonstrate why we're allowed to do that. So now I can go 17 minus 9 is 8. Then we go to do 0 minus 6, and that's a problem, right? So we go over here and try to borrow. Ooh, it's still a problem. So we go over here, and finally we can borrow. So what do I do now? Borrow from that, right? So I make that a 1, and then what? That makes this guy here a 10. But I'm going to borrow from that to make that a 9, and then throw the 1 over here. And the first time a kid sees that, they're like, their head blows up. Like, what? Why did you do all that crazy stuff? Right? So it's just a litter of red stuff. But you and I know, because we've done this before, it's now 10 minus 6, which is 4. 9 minus 9 is 0. 1 minus 1 is 0. So that means I must be 48. Okay. That's a complicated process. However, that's what an algorithm is, a process. It's how we get the job done for big numbers. And so we have to have an algorithm. But it's good to know why. What does subtraction mean? And I demonstrated an algorithm in class the other day called the equal additions algorithm. So I'm going to demo that one again today. It is my favorite, I think. 2017 minus 1969. Oh, I get it right that time. So the way the equal additions algorithm works, switch to blue, is you try to take 7 minus 9, and you realize you can't, and you say, well, wouldn't it be nice if that were a 17? And then you make a note. I just added 10 to the top number. So then you add 10 to the bottom number to compensate. But I do it by putting the 10 down here. So I make that 60 a 70. So this is the idea of equal additions. I just added 10 to the top number and 10 to the bottom number. I'll explain why that works in a moment. 17 minus 9, that works pretty well. There's my 8 from before. Now I want to do 1 minus 7, but I can't. So I say, hey, wouldn't it be nice if that were a 10? Now really, that's a 10 in the tens column, so it's really what? 10 tens, or it's really 100 there. So then I add 100 over here by making that 9 a 10. So I bump it up from 900 to 1000. So I added 100 to the top and the bottom. 11 minus 7 is 4. 0 minus 10, can't do that. So then I bump that up, and I bump that up. 10 minus 10 is 0, 2 minus 2 is 0, so I get the same number, 48. Nice thing about this algorithm, I don't have to scurry all the way across and then all the way back when there's not enough stuff to borrow, when there's zeros in the way. I just take it one step at a time at each part. Now you may look at that and say, that is weird, I don't want to do that, it's not what I learned. However, it has pros compared to this one. On the other hand, there's other problems where this algorithm has pros compared to that one. Everything has its pros and cons. Two different ways to do it. So let's call this algorithm over here our standard algorithm, because that's what most of you grew up doing. Did anyone else grow up doing subtraction a different way, by the way? Every once in a while I have somebody that went to a school or a different country and did it different. You guys are all with that one. So let's call that standard. It's also called the borrowing algorithm or the regrouping algorithm. This one over here is called the equal additions algorithm. And if you watched any of the videos, there was a short, like 2-minute clip where a guy on the Pearson website demonstrated the equal additions. He did it a slightly different way. When I do it, I just focus on 10 at a time. I find that pretty easy. He added whatever I needed to make this a 0 and then that a 0. I don't know if anybody watched that one, but I highly recommend it. You all know how to get to the videos, right? How do you get to the videos? Pop quiz. You can see the, yeah. So there's a link in the Pearson section to the multimedia library. So you go to the multimedia library and you search. And there's also a link in a different spot to my YouTube videos. So there's 2 places you can grab videos for this class. So that's called the equal additions algorithm. It's just a process. It's a series of steps you follow to get the job done. Whereas a model generally requires you to use some toys or draw a picture. Okay. Do we really want to draw a picture of 2017? Not really. No. Okay. So models are a big thing we're going to look at for each operation. Algorithms are the next thing we look at. Another big idea with all whole number operation are certain special properties that they have. So we're going to linger on properties for a little bit, and then we'll come back to models and algorithms. So a property is something that's common throughout the system. So for example, is there anything special about addition that you recall? Something we might call a property of addition. Like, what's the easiest number to add? What's it?
10.
Not 10.
1.
Not 1, even easier. What's that?
0.
0, yeah, 0 is the easiest number to add. You pick any number like 7, you add it to 0, it's still 7. If you take 0 and do that first, it's still 7. 0 and this set of operations there give us what's called the identity property of addition. No matter what I add 0 to, that number keeps its identity. It doesn't change. Later, once we get a little more work done, that leads us to another property called inverses, but we're not quite ready for that. Another thing, notice how I did this in 2 different orders. Does it matter the order you add numbers? That's a property. Anybody remember the name of that property?
Closure property.
What's that? Not closure. We'll get to closure in a minute. Commutative. Yeah. Commutative. So, for example, 3 plus 2 is 5, and 2 plus 3 is also 5. This is called the commutative property. Does anybody live here on campus? housing. Of course you do, right? You commute to campus, true? And then you have to commute home. So the commutative property, commute, means to move. And notice these numbers have to move places, but it doesn't matter that they move. It's still okay. Do all operations in arithmetic have the commutative property? No. For example, we know that 5 minus 2 is equal to 3. But what about 2 minus 5? What if I try to change the subtraction? What happens there? I get a negative number, which isn't even a whole number. It's like, what the heck is that? So this does not, subtraction is not commutative, because you can't pick them up and move them and still get the same answer. So subtraction is not commutative. So we've got the identity property. Nikki brought up the closure property. I'll come to that last. That's a weird one, but an important one. There's another property where you can change how you group things. So for example, 2 plus 3 plus 7 versus 2 plus 3 plus 7. Order of operations says you should do the 2 plus 3 because order of operations says go left to right as a general rule. So it kind of implies there's a parentheses there. Question, does it matter if I put the parentheses around the second two numbers? Okay, everyone's shaking their head. No, let's just double check for fun. Order of operations says you really ought to do it this left way. So 2 plus 3 is 5. Then add 7 to get 12. Over here, I changed the grouping with parentheses. Order of operations says you should do what's in parentheses first. 3 plus 7 is 10. Then add the 2. I still get 12. Since these guys match, that's a special property. It's called the associative property. So the parentheses allow us to change how the numbers are grouped or associated. So associate just means group stuff. So commutative, you have to physically move the numbers. I didn't move any numbers here. All I did is change the grouping with parentheses. So that's associative property. Is subtraction associative? Ooh, Caleb, what's up?
I'm just curious, like, what's the difference between the identity property and the commutative? Because you have like 7 and 0 and then 0 and 7. It's like the same thing as...
Yeah, so identity property, the key here isn't the fact that I switched the order of them. It's the fact that I have a 7 here and I still have a 7 there. Oh. 7 retained its identity. So the identity property basically says 0 doesn't change sums. You can add it all you want, doesn't change a thing. Okay. So 7 retained its identity when I added 0 to it. It did not change. And usually it doesn't matter where you put it in, it still doesn't change stuff. With subtraction, because subtraction is not commutative, we generally say subtraction doesn't have an identity because you can't change the order. Okay. But we know if we subtract 0, nothing happens. So 0 is special there, but it's not as special as with addition. Where are we? Okay, so Nikki brought up an idea called closure. So at the moment, we're mostly talking about addition, a little bit of subtraction. And not only are we talking about addition, but we're only working with whole numbers for the moment. To talk about the idea of closure, you need an operation like addition, subtraction, multiplication, division, power, something like that. And you need a group of numbers to work with. Here I'm working with the whole numbers. And what closure means, if you start with whole numbers, you end with whole numbers. Okay? In this case, at least. So Ashley, what's your favorite number?
6.
6. Ooh, that's an interesting pick. And then Caleb, what's yours?
7.
7, okay. What's 6 plus 7?
13.
Is 13 a whole number? Yeah. So I started with whole numbers, I added them, I ended with a whole number. So the question is, if I always start with whole numbers and I add them, will I always get a whole number answer? Yeah, so then we say addition of whole numbers has closure. Addition is closed with whole numbers. It means we always get a whole number answer. So check. Let's see if subtraction is closed. So Tiffany, so we got subtraction of whole numbers. What's your favorite whole number?
8.
8, excellent whole number. Mine today is 48, because I just turned 48. So what happens if I take 48 and subtract 8? What do I get? Is negative 40 a whole number? Nope, not a whole number. So is subtraction closed? Nope, because I can get numbers that aren't in the set I started with. Okay? So subtraction is not closed for whole numbers. Now that doesn't mean there isn't some set out there it's closed for, but it's certainly not closed for whole numbers. So you think, well, what other kinds of numbers are there? Well, there's a group of numbers called the integers. Does that sound familiar? So integers are their whole numbers and their opposites. We'll look at that in a chapter or 2 from now. But I just want to mention integers are the whole numbers and their opposites. Okay, so then we have to decide what it means to be an opposite. My version of an opposite, it's what happens when you multiply by negative 1. So if you start with 2, the opposite of 2 is negative 1 times 2. Well, that means we have to know how to multiply whole numbers, or multiply by negative numbers, which you guys all know that's what we call negative 2, right? So if I change my set from whole numbers to integers, now could subtraction be closed if I work with integers? Well, if I subtract 2 numbers, the answer is either going to be positive, negative, or 0, right? So yeah, I think subtraction would be closed for integers. So closure is a special thing. It works with some sets, but not with others. Addition is nice. We start with whole numbers, we end with whole numbers. Subtraction, a little more complicated. We have to get the idea of signed numbers so we can get the integers so we can have subtraction being closed. Are you going to talk about closure with your kids? Sort of, kind of. I mean, it's going to come up. Kids are going to want to do things like 2 minus 3 because they did 3 minus 2. And then ultimately, you're going to have to talk about what that really means. So you get there. All right, so properties. We've got closure, associative property, commutative property, and identity property. So those are for addition. Subtraction kind of sort of has an identity. It's 0. It doesn't have commutative. It doesn't have associative. And at the moment, it does not have closure because we're stuck on whole numbers. Okay. However, there is a nice relationship between addition and subtraction. And this is an idea called fact families. And so I'll pick on 2 plus 3. We know that's equal to 5. So there's a whole family of facts related to that one statement. This says maybe Gary has 2 bicycles and Ashley has 3 bicycles, and together they have 5 bicycles, right? So the set model. We could talk about Ashley's bicycles first and then Gary's. Bottom line is they still have 5. So because of commutativity, that's another fact in this family. However, it's the end of the day, Ashley's going home, is she gonna take her bicycles with her? Right, so that illustrates the idea that 5 minus 3 is 2, right? Same numbers, now with subtraction. So these two facts, I think, are related because if we read this addition fact backwards, we get this subtraction fact. What other fact can I pull out of this? 5 minus 2 is 3. So that's kind of like reading this one backwards right there. So 5 minus 2 is equal to 3. So generally, with a group of numbers, we can put them together with addition or subtraction. There's going to be 4 facts total in that family. And playing around with fact families can do things like, what would I add to 2 to get 5? Right? And if we're very familiar with the, 2 things and 3 things is 5. So yeah, 3 would be the answer here. We talked last time about the what do I add idea for subtraction. What would I add to 2 to get 5? And that's ultimately a subtraction problem. And so fact families are a way to help us relate those. All right. Let's see. We did Hindu addition last time. I think we did lattice. I'm pretty sure we did not do scratch addition. Does that sound familiar?
I think we touched on it, but didn't do.
Yeah, I might have mentioned the word, but I don't think we did it. So scratch addition is pretty cool. It's mainly used when you have a whole bunch of numbers to add up. Like suppose I had to take 23 and 35, 17, 12, and 36, and I had to add them up. Okay? And this comes up in a variety of circumstances in our life when we have a whole bunch of things to group and add like that. Does anybody kind of lose track when they're adding a big list like that? Right, I do all the time. So here's the way scratch addition works. You think about groups of 10 because that's our number system. Every time you make a group of 10, you make a scratch. So for example here, 3 and 5 is 8, plus 7 is 15, scratch, because there's a 10 in that 15. Then I only worry about the 5 from the 15. So from here, 5 and 2 is 7, 7 and 6 is 13, scratch, right to 3. What do those 2 scratches mean? Meant I found 10 twice. In other words, these numbers added up to 23 because of those 2 scratches. Okay, so it's just a way to keep track so you don't have to worry about climbing higher and higher in the numbers. And then just come down and do the same thing here. 2 and 2 is 4, 7, 8, 9, 10, 11, 12. So I scratch. Not much need to, write the 2, scratch comes down as a 1. So those numbers seem to be 123. Okay, so it's this, every time you make a group of 10, you make a scratch. So the number of scratches is what gets carried to the next column. That's scratch addition. Kind of cute. Okay, let's take a look at subtraction again. And just a review of the models that we came up with. Remember, models explain why we should get a certain answer. Most common model is called the takeaway model, where we show one group and we physically remove stuff to get what's left. 2 is the comparison model. And we worked on these in activity 2. So let's bring that up for a peek. So in the first example here, they're showing what takeaway looks like for, say, 34 minus 12. So we start with 1, 2, 3 10s and 4 1s, so there's our 34, and then we just cross off 12, a 10 and 2 1s. And then we just make a note what's left. Well, there's 2 10s for 20 and 2 1s for 2, so they're 22. It becomes complicated when we have to borrow, and a lot of kids struggle with borrowing, and so starting them off with blocks is a good way to proceed. And we played around with drawing these pictures a week ago. So here we're going to demonstrate 43 minus 28. So first we have to show what 43 is, 4 10s and 3 1s. And we make a note here, well, we can't, there's not 8 1s to take away, right? That's not going to work here. So then we take one of those 10s and trade it in for 10 1s. That's the act of borrowing, okay? So here we just call it trading in. Now I can cross out those 8 1s and my 2 10s, and then I can see what's not crossed out. So I can see there's a 10 and 5 1s, so the answer's got to be 15. Right? So physically handling the blocks can help the kids better get used to that carrying, which looks bizarre when they first do it. And so in your work on this one, you want to link the subtraction problem you're doing to a picture of the blocks that you're playing with. Okay. Now, it's going to look different when we do a comparison, because we're not taking anything away with comparison. So here's an example of 42 minus 27. Now notice in this model right here, we have to show both the 42 and we have to show the 27 because we want to try and match them up. Are there enough ones to match up here, top and bottom? Not enough. So then we have to do a trade. Instead of 4 10s, we now have 3 10s, and then we take one of those 10s and trade it in for a bunch of 1s. And what they did here, it's kind of hard to see on the screen, but you guys got the papers in front of you, hopefully. Zoom in a little more. They then just picked up and laid the 27 on top of the 42 to see where they matched up. And we can see where they didn't match up, it's lighter in color, and so there's our 10 and 5 1s there. So the picture looks different. Nothing is getting taken away. We're just comparing two different sets. With the takeaway model, we really only draw the first set. If you look back here. So we're only drawing the 43, and then we just cross off the other set, right? We don't draw them both. And so you're going to attempt to draw those pictures if you haven't already. Okay, so let's try some more alternative algorithms. Let's see, we're not done with models. Sorry, 2 more models here we talked about. Another model was the missing add-in model. I called it the what do I add model. And it's basically a comparison model when you draw it out. So for example, if I wanted to demonstrate 5 minus 3 equals what, instead I pretty much take it backwards. So in reverse order, it's what plus 3 equals 5. So now I'm comparing 5 and 3 to see how are they different. So here's my 5 things. And here's my 3 things, and they match up everywhere but with those 2 pieces here. So it's like a comparison leading me to an answer of 2. And so that's called the missing add-in model. It's like a comparison model, but written down a slightly different way. Does anybody remember the last model we did for subtraction?
Number line.
The number line model, right? Yeah, so the number line model is another one we can use. So with the number line model, we have to have a number line starting with 0. And there's a couple of different versions of it. If I wanted to demonstrate 5 minus 2, or 5 minus 3, just doing. On the number line, I would start at 5, and subtraction means go backwards on the number line. So from 5, I want to go backwards with an arrow 1, 2, 3 units and see where I end up. And this is a pretty popular one in schools because kids generally are going to have a nameplate on their desk with a ruler on it, so they can use that ruler to count out and do their additions and subtractions. So it's kind of like counting on our fingers. It's an excellent tool, good way to do math. All right, algorithms. So I just want to develop an algorithm. I want to consider the comparison model. And the comparison model asks, how are two numbers different? And a number line is kind of a nice way to look at this. So I'm going to put another number line up. And let's consider the problem we were just looking at. I have the number 5, which could be designated by that arrow, and I have the number 3, which is that arrow right there. So here's my 5, here's my 3. So they're alike where they overlap, they're different where they don't. And they don't overlap right here. So they're different by 2. Now, the cool thing about the difference, so one thing subtraction does is it tells us how far apart two numbers are, right? When we talk about the difference of two numbers, we're saying how far apart are they physically. If I pick these two numbers up and I move them down the number line each by the same distance, they're still going to be the same distance apart. So for example, if I were to add 10 to both of these numbers, then instead of 5 minus 3, I would have 15 minus 13. I move them both along the number line, 10 units. How far apart are they? They're still 2 apart. Suppose I move them both down the number line 7. So instead of 5 minus 3, let's see, 5 and 7 is 12. 7 and 3 is 10. They're still 2 apart. So as long as I move them down the number line the same distance, they're still going to be the same distance apart. You with me on that? This is where the equal additions algorithm comes from. As long as you add the same number to both the top number and the bottom number, the first number and the second number, they're still going to have exactly the same difference. And there's a couple of different ways to apply the equal additions algorithm. So I'll go over both of those ways here. New problem. Suppose we had 23 minus 17. So at the moment, 3 minus 7 is a problem because I can't do that. But what I could do is bump this 7 up 3. Why would I pick 3? It turns at 20. 20 is a nice number. So that's going to give me 20 in the bottom. But I'm going to change the difference unless I do the exact same thing at the top. Move it along the number line the same distance. And so now I have 26. Which subtraction is easier, the 23 minus 17 or 26 minus 20? Well, the 26 minus 20 is easier. So then I get, oh yeah, there's the difference of 6. Now we teach kids to count up from 17, but that's, when you try teaching that to young kids for the first several months, they just struggle with it. Where do I start again? 23, 24, 25. I mean, they get all messed up. Where to start, what to start counting at. But, counting up from 17 on our fingers, we would go 18, 19, 20, 21, 22, 23, and see we had counted out 6 fingers. Pretty complicated. Here we can just say, let's bump that up a little bit. Let's bump that up a little bit. So one version of the equal additions is where we just pick a convenient number to make the bottom numbers easier to work with. Do the same thing to the top number, and you'll be okay. And this was covered, it's covered in the book and it's covered in activity 2. I went over a different version of this a few minutes ago, so I'll just do that other version. In my version of equal additions, I don't do 3s and 7s, I only do 10s for my equal additions. And so what I would say is, well, I can't take 7 from 3, so I would make that a 13. So I just added 10 there. So I add 10 to the bottom number, but I do it in the next column. I make that 10 a 20. So I just added 10 to top and bottom. Now I can conveniently say 13 minus 7 is 6. 2 minus 2 is 0, so the answer must be 6. So that's another version of the equal additions algorithm, where you just work with 10s instead of convenient numbers to get zeros. All right, other algorithms. I did this one last time. Hindu, instead of how we start in the 1s and work over, so we go from right to left, they go from left to right. And we can do that here with the 23 minus 17. So the way we would attack this left to right, we would say, okay, well, what's 20 minus 10? Well, it's 10. Then we try to take 7 from 3. Can we do that? No. Since we've already done this column here, we have to borrow from below. So I have to borrow from there in order to make that a 13. And then I can come down and say that's a 6. So the Hindu algorithm, we have to borrow from below. Let's try that again. Suppose we had 392 minus 75. So we would start on the left side. 300s minus no hundreds is 300. 90 minus 70, or 9 minus 7, gives us 20, or 2 in the tens column. And then 2 minus 5 is a problem, so I have to borrow from below. So I take a 10 away from that and bring it up there. 12 minus 5 is 7, so the answer must be 317. So we went left to right instead. And there's a large part of the world that does it that way, instead of how we do it from right to left, where we carry and borrow from, we borrow from above. They have to borrow from below because of the direction we're moving there. All right, another algorithm is the low stress algorithm. So let's go back to our 2017 minus 1969. The way the low stress algorithm is, you rewrite it with some space in between. So I take my 2017, a lot of places they'll put a big rectangle in there and then write the 1969 underneath. And then they just kind of do the regrouping in the box, so it's not as messy with all the scratching that we do above. So I just kind of look and say, well, I know I can't do that, so that's going to be a problem. So I have to start looking over here to borrow. Okay. Well, I can see I have a 10 there for my 17, but then here I have a problem. So I realize I'm going to have to borrow over to the 20. And so I start crossing stuff out and then start writing it underneath. And let's see, I took that one away. So I'm going to have a 10 there. So we rewrite, instead of having all the messy scratches, we have 17 ones. We rewrite this as 10 tens, 900 to 1,000. And that's supposed to help kids deal with that mess we created before. Because if we look back, where do we have that one here somewhere? Way back. There we go. Yeah, so this is kind of messy over here. And any kid that has trouble focusing is going to struggle with that mess. So this is a solution some books use to try and make it a little neater. And so then we can come down and say 17, take away 9. That's our 8. 10 minus 6 is 4, and then 19 minus 19 is 0. And so it's just our 48 there. That's called the low stress element. All right, let's pause there for a moment. That handout I gave you on algorithms, take a look at that. I put that on the website here. So I'm not going to go over all of these algorithms, but I'll go over many of them. So the goal here is you got to learn, the models are super, super important. Those are the most important part of this whole chapter. Like, why do we get the answer we get? How do we concretely show kids that? You're pretty much stuck teaching the standard algorithms because that's what we do in this country, right? So you're going to carry, you're going to borrow, you're going to do multiplication a certain way and division a certain way. However, you're going to have kids on the low end that really struggle to borrow and carry properly, kids that really struggle with multiplication or long division. So it's nice to have ways that might work better for some kid. Like a kid that's really struggling with borrowing with zeros in the top might really get a lot out of the equal additions algorithm or the low stress algorithm. Kids that are messy might really like the lattice algorithm for addition I showed the other day. We'll do a multiplication version of that today. For you guys, what I want you to do is know how to use, you all know how to use your standard algorithms. The point of the activities is to learn how to explain why they work the way they do. So for our standard algorithms, you need to show me with pictures why they work the way they do. The other algorithms here, you don't have to tell me why they work. You just have to be able to demonstrate that you can use them. And so generally what I'm going to require is you're really good with the standard one, and then you pick any two in each grouping and you learn those algorithms. So on the test, I'll ask something like, here's a subtraction problem, show me 3 different ways to subtract. And of course, most people will pick the standard way and then show 2 other ways that you like. Like maybe you like the Hindu one, maybe you like the complement, maybe you like the absurd algorithm. For each of the algorithms I list here, in the body down below, I show step by step what to do to get the answer and describe what I'm doing as I do it along the way. When you write it on paper, your paperwork would look pretty much just like my last part. You wouldn't write it up in stages. It all happens kind of, you know, in the same spot. But I usually break it down step by step. So I've got a bunch of different algorithms here. The complement subtraction is pretty cool. I highly recommend you look at that one. And if anybody wants, I can go over it next week. But for now, I'm going to move on. So there's multiple algorithms listed in the activities. There's multiple algorithms listed in the book. Some of them I repeat here, but mostly what I have here are algorithms that are neither in the book or the activities, just to give you a little more variety, that there's a lot of ways to do this around the world. Okay. So let's see, have we beat up subtraction enough yet? Oh, I didn't go over the 10 frames yet. I need to do that. We did properties. Okay, let's talk about the point of the 10 frames. So you got that other packet of stuff that I called the 10 frames. So I mentioned the other day, when working with numbers, people can visually recognize 2, 3, 4, 5, just if they see something like a group of 5 people, they're pretty sure that's 5 people. Once it gets beyond that, we have to pretty much count to recognize how many things were in that group. So early on, when kids are learning how to do arithmetic with small numbers, it's good to give them systems for organizing stuff. And the 10 frame cards are one way to do that. So what I'll do in classrooms is I'll print these on cardstock. I'll cut them up so we'll have cards based on these. And I gave you 2 papers, right? One should have the partials 0, 1, 2, 3, 4, 5 up to 9, and then the other page should have a full 10. And so kind of like you have playing cards in a deck, like poker cards, these are just a simpler version of that where we have groupings by 5 so they're easy to recognize. And what's nice about these cards, playing around with addition and subtraction, is you can hand the kids these cards and say, okay, what happens if we add 7 to 6? What do I get? And can you see how the kids could pretty quickly look at this and get an answer? Because they can go 5 and 5 is 10, 11, 12, 13. So they're set up in a way that you can kind of visualize and quickly get that answer. So think about this for a minute. What is 7 plus 8? How do you know that? You counted? So a lot of times when I'm doing multiplication, when I'm doing addition, I actually see a pattern in my head, right? So like I see the 8 and the 7 sit next to each other. So here's my 8 and my 7. And I see the 3 from the 8 here join with the 7 to give me a 10, and there's 5 left over. And visualizing math is super important for kids making progress. There's studies that show the more kids play with blocks like Legos, anything they can put together, even just wooden blocks, that builds up this visualization in their head to better do math, science, engineering type stuff. So these are just a simple way to kind of get kids to visualize those sums. So what I'll do a lot with kids that are struggling to remember their addition facts is you could take these cards and you could play addition war. So each kid gets a set of cards, you shuffle them up, and 2 kids throw down cards. And the first one to say what it adds up to is the winner, and they get to take the cards. Okay? Now, you got to be careful when you do that because you don't want to pair up a kid that's really fast with another kid that's a little slower because that's going to be awfully frustrating. So you kind of want to pair them in groups. If you're helping a kid, then what you do is like I handicap myself. So I have to count to 5 or count to 10 in my head before I can state an answer to give the kid a chance to kind of catch up. So often you'll have classroom aids, and so this might be something you could do to help those kids that are struggling with basic facts. Because it's really hard to do these algorithms if you can't remember what 7 plus 8 is, and you're always counting on your fingers. There's some people that just don't proceed past that, and then we just need to help them however we can. But visualizing patterns can help a lot. So the other 2 pieces of paper I gave you here, and I'll post these on the website, I didn't get to that yet, are some things that could go home with parents. So I have a bunch of different games that you could play with either the 10 frame cards or with regular playing cards. Make it 10 solitaire, nifty 9s, excellent 8s, and these kind of describe those games that kids and parents can play together, or kids can play with other kids. And then I gave another one that's my usual take-home sheet, card games for home. And so there's just some other games listed here that kids can play around with. So these are just ways I use playing cards or base 10 cards to try and get young kids to get better at visualizing arithmetic. So these are kind of targeted at 1st, 2nd, 3rd grade in terms of playing around with the kids to get what we call number sense, which is just, you know, an idea on how things work together mathematically. Okay. I'm going to